I want to begin with a confession. When I first started thinking about ideas in this book, I had no intention of writing a book at all. I was simply puzzled by a question that nagged at me for years. Why do so many different systems in completely unrelated fields seem to fail in the same way? Economists build models to predict markets, and those models work reasonably well until they suddenly do not. Epidemiologists construct careful simulations of disease spread, and they capture broad strokes but miss critical turning points. Machine learning engineers train algorithms using straightforward approaches, then discover they need to add something called momentum to make their systems learn efficiently. Control engineers design systems to maintain temperature or speed or position, and they find they must include a derivative term to prevent wild oscillations. What struck me was not that these problems existed. Every field has its challenges. What struck me was the similarity of the solutions. Across domains that have nothing to do with one another, practitioners kept discovering that they needed to track not just where the system is, but how fast it is changing. They needed to care not just about the current state, but about the trend. This book is my attempt to explain why. It is also an invitation to think differently about how we understand complex systems and about the surprising unity that underlies apparent unrelated phenomena. The journey began with Newton, not because I was out to study physics, but because I realized that physics had already solved a problem that other fields were still struggling with. 3 centuries ago, Isaac Newton established a framework for understanding motion that was proven extraordinarily successful. Objects have positions and velocities. Forces change velocities, not positions directly. Multiple forces combine by simple addition. These ideas are so familiar that we rarely stop to ask why they work. But here's the puzzle. Newton discovered these principles through careful observation of physical objects, planets, cannonballs, pendulums. He had no reason to think that his framework would apply to anything else. Yet when I looked at the problems plaguing economics, epidemiology, artificial intelligence, and social science, I saw the same structure trying to emerge, the same corrective measures being invented independently, the same fundamental insight being rediscovered again and again. This led me to a hypothesis that became the foundation of this book. Perhaps the success of Newtonian mechanics is not a special fact about physical matter. Perhaps it reflects something deeper about how systems with certain structural properties must behave. If that were true, then the Newtonian framework would not just be one useful approach among many. It would be the necessary form for modeling any system where multiple influences combine and act on trends rather than states directly. I spent several years working through the mathematics to see if this hypothesis could be made rigorous. The result was 2 academic papers that established what I call the structural diagnostic principle. In technical terms, I proved that if a system satisfies certain axioms, then any attempt to model it without including velocity as an independent variable will fail in predictable ways. The axioms are not arbitrary. They capture intuitions that practitioners in many fields already hold, that influences should be combined sensibly, that systems should continue their current trajectory unless something acts on them, and that causes should have effects independent of which direction the system is currently moving. But academic papers reach a limited audience, and the implications of this work extend far beyond the technical details. If I am right, then we have been thinking about modeling in a subtly but importantly wrong way. We have been treating the Newtonian framework as one option among many when it should be understood as a structural requirement for certain types of systems. We have been inventing ad hoc corrections when we should have recognized that a deeper principle was at work. This book is my attempt to explain these ideas to anyone willing to think carefully about them. I have deliberately avoided mathematical formulas, not because the mathematics is unimportant, but because the core insights can be conveyed through words, analogies, and thought experiments.